Welcome to Yong tuition. I'm sure you are aware of the incident happened on the internet several years ago. A professor in physics was challenged by a guy who only has a master's degree in electronical engineering. And I was surprised to discover the response, the heated words from this professor. He basically openly says this guy is, oh, you only got, not the original word. It simply says that, well, you just, the guy got a master's degree and how can you challenge me? And in addition, he also, by that, for some reason, I don't know, but obviously he actually directly make a remark that say that there's this guy, actually, I know this guy is electro boom. He said, you actually discredit my lifelong image in teaching physics in university. I think it sounds very overreact, okay. And actually, this is not a simple issue anymore. And imagine if this professor were the supervisor of this the guy who got a master's degree doing his PhD, and can you imagine what could happen? I mean, that is quite obvious, right? Or put it another way, if this professor was the editor-in-chief of certain journal in physics, and what would happen to this the guy who wrote some remark on his idea? So I think this is not a simple issue, morally speaking. So that is why, since I discovered this incident, I had spent hours to watching their relevant talks and relevant reference. And eventually, I think I have found a very effective way to make the final judgment of this open debate. Let's go. The issue is that this Professor Lewin, must have had an idea about how to apply Kirchhoff's loop law years ago. And he got this idea, namely that Kirchhoff's loop law is invalid in the presence of the induced, the current. And he obviously had this idea a long time ago, and would consider this idea as type of the, this as important as a basic law in physics. And so whenever he get a remark, a response from audience or students, by the way, I don't like his lecture very much. He's always talking his idea. He barely asks the audience, the students. He barely encourages audience to get the feedback. I think this is not the way I think the good teacher should behave. Yeah. And he always put his idea, no matter whether it's good or not, as if he's come from his brain. So you have to take care of that. This is not the way to study physics. Okay. So anyway, this is his famous wording that Kirchhoff's loop law is for the birds, for the idiots. But so what's happened? Let's have a close look. What happened? So basically, he's trying to figure out how to apply the Kirchhoff's law to explain some apparent measured fact that the the measurement shows that in this simple loop contains the two resistors in the presence of the changing magnetic field, external magnetic field. And you cannot, in this case, you cannot explain this phenomena by applying his Kirchhoff's laws. And of course, this remark was immediately noticed by electron boom. And I like his response, the way to mention to talk about this issue. Truly, he behaved like a gentleman, and he didn't go to the wording, the theoretical background first. What he did is first doing experiment. That is authentic method. If you want to become a good physicist, you don't debate. If you can, you do the experiment by yourself, or you're trying to dig out other new experiment, which is available. And he came out of an idea which actually consistent with my analysis. He had worked out several ways to refine or to characterize his measurement, and also make his conclusion based on his experimental result. I think this is something we should, as a community, encourage people to do so. Okay, and there's no point to play the cards. You see, I actually dislike the idea that you play the card. I got a poke. You say, what can you do? Yeah, this is what Feynman, Professor Feynman, Richard Feynman has said. This is something Sommerfeld, some people have said. You don't discuss or explore the idea in physics in this way. Okay, so that is why I spend a lot of time on this issue. Now, of course, you know the debate now. So if you have time, you can look their relevant video clip again. Let's just focus on the issue. Okay, so this is the issue. So if you have a closed loop made by a metal wire, and then you will have this experiment set up. If you allow the magnetic field in this time is moving into the page. If you just increase the magnetic field, you would expect that, according to Faraday's induction law, that you would be able to detect some current, clockwise, anti-clockwise in this case, to stop or to resist the change. So there are many there are sufficient basic law in physics allowed people to do so, to explain this phenomenon. So basically, of course, the formal approach is just starting from one of Maxwell equations. And the third one, which is known as Faraday induction law, actually we have to mention the Henry case. Actually, basically, the induction law was discovered by two great physicists. One is Henry, another is Faraday. Actually, the experiment was, this observation was confirmed between 1831 and 32. I think the Henry was the first. And but by the way, Kirchhoff's law was put forward about I think it's 1845. So there's no point to assume to follow this Professor Levin's idea that he says the older Kirchhoff's law has nothing to do with induced voltage or induced electromotive force. Actually, this is something I have to make it clear. Let's return to the question. If you just use the Maxwell equation. This issue is very simple because it got the symmetrical. You see, we have a regular shape of this area, which is circle, and we have well-defined the integral. That's how you do integral. So you just chop this circle into many pieces, and if that piece is small enough, then you can use a constant electrical field to work out that integration. And because it is in this particular system, the integration on both sides became rather simple. So that is the formula. So that is formula E induced by the changing magnetic field in this experimental setup. As you can see that this electric field is independent of the resistivity of the wire. So in this wire, I have deliberately draw a different resistors. Can you see the color, the purple color, and it is a dark red color, represent different part, have different wire, have different resistivity. But the integration don't care. When you do integration, we are trying to work out essentially the voltage, okay, not the dynamics of local electron. We are talking about the potential difference established due to the varying magnetic field. So that is why this is something very important to remember, that these induce the Ampere laws, or the Faraday's induction law, can be used to describe this phenomenon perfectly. Okay. But understandably, the trouble is that how do we incorporate this induced voltage into an equation? That is issue. That is issue. So let's look at this real circuit. You see, so in this real circuit, at the same scenario, we know that we can build up. We know that the current were formed due to the induction, and so therefore, but without incorporate a power supply explicitly, it would appear difficult to write a proper equation. Can you see that? So how can we solve this problem? Okay, on the one hand, if you just follow the Kirchhoff's law, and you wouldn't be able to incorporate the power supply. On the other hand, according to induction law, the origin of the current must due to the change in the magnetic flux across this circle. So that is issue. Okay, unfortunately, both of them failed to notice this is the key issues in this debate. In a real circuit, it's challenging. It's if not totally impossible to incorporate this invisible battery, because remember that in this scenario, unlike the ordinary battery, the voltage induced by the change in magnetic field is distributed evenly everywhere in this loop. Okay, so what can we do? Well, in physics, it's very important, as I emphasize to my students many times. So in physics, we are not dealing with real stuff. Physicists only deal with models. Okay, so it is art to introduce the model to tackle the real issues. So in this case, if we just instead of considering this real circuit, why don't we consider a model circuit in which the battery is visible? So here I simply use the one battery. It's just a symbol to denote the voltage generated by the changing magnetic field. Of course, this is what we call equivalent circuit. In real case, that the voltage is not necessarily located at this particular point. But this is not, this is irrelevant, because the idea is that by just draw this diagram, by making this invisible battery invisible, and we can simply use Ohm's law. We don't have to invoke Kirchhoff's law. What's the point to use Kirchhoff's law all the time, knowing that there's a basic law called the Ohm's law? So the Ohm's law in this simple DC, you can consider as instantaneously. Is in this simple circuit, you can simply write the equation by incorporate the induced the voltage as effective battery into the equation. You know what I mean? So this is not the only way to visualize this battery. In order to explain their debate, the measurement, then we have to we can also alternatively divide this battery into two. Can we? Of course, we can, depending on the question. You see, that is what the model for. So the model makes the argument not just convenient, but also quantitative. So in this case, I have deliberately divided this equivalent battery into two equal parts, so that we can talking about the voltage, the potential difference between point A and B and A. So based on this diagram, it's straightforward to make this. Oh, by the way, from the first equation, we can immediately work out that the potential, the voltage induced by the induction is equal to the sum of the two voltages across the two batteries. And furthermore, if we assume that the battery have a certain ratio, so the R is 9 times, the R2 is 9 times, and the R1, then we can get this simple relation between the two voltage drops across the two batteries respectively. Now, based on the second diagram, we can easily using the way to work out the potential difference to these two equations. You see, these two equations you can work out from the circuit to circuit. Second model. By incorporate the special arrangement, then we can easily work out that the two voltages are indeed the potential at A and B are indeed different, quantitatively different. Okay, actually, these two equations give the same result. That's to say, the voltage, the potential at point B is higher than the voltage at potential A. So certainly that these two potentials are not equal. So that is the basis. That is how to incorporate. If you prefer, you still can using the Kirchhoff's law. Okay. Of course, the basic idea to introduce this model to visualize the battery, the power supply, can be extended to more complicated finite elements. Okay, so basically, one can consider the total effective voltage due to induction can be considered a sum of many parts. But bear in mind, they must equal evenly. So that's why in third model, we can also distribute this effective battery at 4 positions. That would allow us to work out the more sophisticated experimental setup. Actually, that was proposed by Electron Boom. And to explain his experimental result, we can go that way. So that is one of these. I use the third model to explain the experimental setup by the electron boom. So if the yellow colored loop, the half loop, represents the cable that he used to trying to measure the voltage across the A and B, but it's turned out that the measured voltage, he called it, I use this consistent notation, it's called the VS1, because the display on the cystoscope or cystoscope, which gives the reading is actually exactly equal to the voltage across this first resistor. Why? Because according to this model, you can assume here we have, in real case, this the yellow circle is semicircle is very close to the orange one. Okay, but just for the argument, for the convenience to get off the quantitative explanation, we can just you see. So if you want to work out the potential difference between this measured experimentally, you can just follow this curve. Can you see? This is first battery, which is quarter, and then that is a battery opposite. And then you cross that the resistor close near the measurement. So that is how I use this simple diagram to get this equation. Indeed, in this case, what you measured is actually the voltage near on the side, actually close to this side, on the left-hand side. In other words, although the setup is made, the pickup is from A and B, but what you measured in this case is equivalent to is equivalent to put this probe at the two terminal of first resistor. Okay. Furthermore, you can discuss a variety of scenario. I hope and Electroborn would watch this video, and so that he will do more experiment. Okay? That is the way how we study physics. Okay, and physics is not a rigid body. Physics is a dynamic itself. You have to the experiment, by the way, is the most important one. Remember what happened in history, and Aristotle's physics has been there for over nearly 2,000 years. And it was not until Galileo who he challenged his idea by doing experiment. So that's happened exactly this time. Okay, so I hope that someone or the Electroboom himself will come out with some new experiment. So this is my prediction. In this case, if this is his original proposal to measure the local voltage, now based on my analysis, you can actually extend this probe to the other side. At the end of the day, you still measure what you have measured. You still got the resistor of the first voltage of the first resistor. So there are many scenarios you can go. And I think I'm not going to make this video too long. By the way, also, without this, using this visualization proposed by myself, that actually Electroboom had approached the truth by actually readjust the location of the two resistors. That's what he do. So basically, he can put this resistor, that's actually his experiment setup. So that is experiment setup. So what he did is that he put the two resistors outside the circle and very close. So this area is very small. So in this way, he can confidently measure the effective voltage induced by the changing magnetic field. And this setup was eventually found out by himself. But alternatively, we can also use some thought experiment. You see, first of all, can we just remove these two resistors outside the circle, knowing that the cause of the induction is purely due to this the evenly distributed circle. So in this way, we can simply work out the equivalent circuit as well. So that is a method I used to make this final judgment. Okay. There are other issues I'm not going to detail. Perhaps I just discovered during the preparation of this talk, but I think I should stop here and need to make a comment, and then we can discuss the relevant issues furthermore. As you can see that Veritasia's big misconception about electricity has opened a door to discover other misconception in understanding electricity, at least in teaching electricity. So please give me, if you could you please like, make and subscribe, and so that I can make more in-depth analysis of relevant issues. Thank you and goodbye.